Hello. In the last class, we have seen how to convert a sine wave or a triangular wave into a square wave, which can be applied at the input of a clock, at the input of a counter, so that we can measure the frequency. In particular, we have seen what is the problem if the input signal is noisy and how we get rid of that using a Schmitt trigger. In the previous class, we have studied the functional behavior of a Schmitt trigger, okay, how it acts or what it does. We haven't seen the circuitry or the realization how a Schmitt trigger is made. So, let us talk about that in this class. Okay. So, the topic is Schmitt trigger circuit. You may recall that in an additional video, we actually have seen this while studying op amps, and I just have mentioned that Schmitt trigger is nothing but wrongly connected amplifiers, inverting or non-inverting amplifiers. Okay. So, let us first draw inverting and non-inverting amplifier. So, let me draw the op amp plus minus. You can give the input here, you can give feedback to the negative side, negative input like this. This is VO, this is, call this R2, R1, this is grounded, which means this is what? This is a non-inverting amplifier. Non-inverting amplifier. Okay, right. Now, let me also draw side by side the inverting amplifier. This is the feedback resistance, this is the, call it R1, R2. Let me give the input here, like the input here, and this is output. This is what? This is inverting amplifier. These are correct circuits. Okay. Now, I will draw wrongly connected, oppositely connected amplifiers. What I will do? I will simply make this minus and this plus. Okay. So, let me make it minus and make this plus. So, now this is no longer a non-inverting amplifier. Okay. We have done detailed analysis why this is no longer an non-inverting amplifier. Output will no longer be proportional to input. Now, in this circuit, output can take only two stable values, which are either this V supply plus V supply or the minus V supply. These are the only two stable values of the output. Output will not take any other value between this plus and minus V supply. Okay. So, this is not an amplifier, but this is Schmitt trigger. Okay. Similarly, here also if you make this opposite, make this minus, make this plus, this will no longer be a inverting amplifier, this will become also a Schmitt trigger. Here also output can take only two possible values, two possible stable values, V supply and minus V supply. Okay. So, note for both these type of Schmitt triggers, they both will act as a Schmitt trigger. There is a small difference which we will study soon. Okay. For both of them, VO can take only two stable values plus V supply or minus V supply. Okay. So, I request you please go back in one of those videos where we did a detailed graphical analysis, I mean with drawing the static characteristic of an op amp. We solved how the output, what should be the output voltage. You may go back to those videos, that will be helpful, I guess. Okay. But let me also tell you very quickly, let me give you some intuition here. Consider this circuit. Okay. If I give, say, some, okay, let us do the analysis this way. Let us take it for granted that output can take only these two values, okay, positive V supply or minus. Let us take it for granted at this moment. I will justify later. Okay. So, assume VO is equal to plus V supply at some moment, okay, at some moment. So, at this point, what can I write? V supply positive. So, what will be the value of the voltage at this point? Let us apply potential divider rule here, because no current goes in this branch, this current is 0, you know. So, this is 0 volt. So, this is V supply. So, this will be V supply divided by R1 plus R2 multiplied by R1. Okay. So, this is the voltage at this point. Now, I give some input here which I can change. Okay. Also say input is changing. Now, if the input is, say, 0 volt, okay, if I make the input equal to 0 volt, what will be the output? Say if this is 0 volt, this is positive, this is also positive, right? This is positive, so this is also positive. If R1 equal to R2, then this is nothing but half of this, so that is also positive. So, this is always positive. If this is positive, so this is also positive. So, this point is at the same value like this and is positive. Now, if this is 0, this is positive. So, V P is at a higher value than V in. So, output will be positive V supply. So, it will remain at positive V supply if I make this equal to 0. If I make it lower than 0, if I make it lower than 0, okay, let me also write what I just said right now. Input equal to 0 volt implies VO equal to V supply. Now, if I take input equal to less than 0, so this is negative, this is positive. So, Vp is at higher value, and if Vp is at higher value, what is the output? Output is positive. Okay. So, then let me write input less than 0 will also imply output equal to V supply. If I make the input, say, slightly positive, okay, slightly positive, slightly positive input, then what will be the output? This is positive, but this is slightly positive, and so if this is more positive, the output will be still positive, because as long as this is at higher potential, the output will be positive, right. So, if input is slightly positive, output will remain at V supply, will not change. But now say I make the input more and more positive. Okay. So, I make it more positive, then it depends whether this input is greater than the current value of V p or not. Okay. If the input is less than the current V p, then output will remain positive. But if I make input higher and higher, more and more positive, then at some value this V n will be greater than V p, and then the output will become immediately negative. Now, let me ask, at what value of the input this output will become negative? Okay. So, question, for what value of input V o will become negative? This is the question. What is the answer? The answer is simple. The input has to be greater than the value of V p, which is this. Okay. So, answer is the input must be greater than this value, V supply multiplied by R 1 divided by R 1 plus R 2. If the input is, so this is the rule, if the input is greater than this value, this is a positive number, okay, because V supply is right now, this is output is positive. So, a positive value is coming here. Now, if I make the input more positive than this, that means V n more positive than V p, then output will switch immediately from a positive value to negative value, right. So, this is the boundary or transition value, this is the value of the input. If you make the input beyond this, more positive than this, output will become negative. Okay. So, here I can write the rule, if input goes beyond greater than V supply R 1 divided by R 1 plus R 2, this will make V o negative, V o equal to negative, that means negative V supply. Okay. So, I can, okay, let me write minus V supply. Okay. Fine. Now, then what will happen? Then so now, so the moment when input has gone below this value, above this value, sorry, above this value, output is now negative. So, let me now write that now, okay, now output is negative at this. So, let us see what will happen after this. So, now output is negative, okay, and input has gone above this value. Okay. Now, so if so this is minus V supply. If this is minus V supply, then this will also be minus V supply R 1 by R 1 plus R 2 potential divider rule. and then the same value comes here. So, this is now negative. So, now this is negative. Okay. So, at this moment this is negative and input is positive. Now, say if I am decreasing the input. Okay. So, now I am decreasing, lowering the input. What will happen to the output? Output will change the moment input, which is same as V n, goes below V p. Okay. So, now output will change. Okay, I could write it here. If input goes below, okay, now if input goes below this value, this is minus V supply R 1 by R 1 plus R 2. If input is decreasing and now it becomes lower than this value, then output will change. If this is lower than this, then output will become positive again, because this is lower, this is higher, then output will be positive again. Okay. So, the moment input goes lower than this, output will become positive V supply. Okay. So, that is the rule. So, let me erase. Let me write that starting from starting from the fact that now V o is negative V supply, okay. So, I could ask the same question, for what value of input V o will become positive now. It is now already negative. So, for what value of input it will become positive, and the answer is input has to go below this value. Okay. So, this is the boundary value of the input or transition value of the input when both these are V n and V p are equal, and then if you decrease input further, then output will be positive. Okay. So, for this Schmitt trigger, okay. So, let me write the rule. Output becomes positive if or when input goes below and output becomes negative when input goes above okay. So, let me draw some diagram, time versus say input. Say the input is changing like this, maybe a triangular wave. You can also use sine wave, and say this height represents the value of this V supply. Okay. So, let me call this value as the upper trigger point. Let me just give it a name, upper trigger point, say, and let me call this value the negative V supply, oh, this multiplied by R 1, R 1. Okay. Let me call this as LTP, say. Okay. So, let me denote this height, say this height is same as this UTP, okay, and say this height is LTP, right, and then how will the output be? Output. So, you see at this moment output is input is crossing the upper trigger point, it is going above this. So, output will become negative. So, at this moment output will become negative. I do not know what it was before that, but at this moment it will surely become negative, and it will remain negative until and unless here input goes below this lower trigger point. Okay. So, here, and then it will become positive. So, at up to this point it will remain negative. Negative means minus V supply, and here it will become plus V supply, and it will remain so until and unless I reach this point when it will become again negative. Okay. So, this is how this circuit works. Okay. And let me call this, as circuit 1. Circuit 1, and let me call this as the other one, I will call it as circuit 2. So, what I have done here, this is for circuit 1. Okay. Just observe, so this is for circuit 1. Observe for circuit 1 again. The output decreases when input increases. Similarly, here output increases when input decreases. Output increases when input decreases, and output decreases, goes down, goes low when input increases. Okay. Opposite behavior, input increases, output decreases, right. So, we call this as a inverting Schmitt trigger. Why is inverting? Because when input increases, output decreases. Okay. This is called an inverting Schmitt trigger, which is nothing but wrongly or oppositely connected non-inverting amplifier. Okay. So, we did the analysis for this. Now, let us do the analysis for this circuit. How will this behave? Okay. Let me start writing from here. Once again, I will my approach will be very similar. Okay. So, my approach will be I will take it granted at this moment that output can take only two stable values, positive V supply and negative V supply. I will justify that later. For now, let us assume output can be either positive V supply or negative V supply. So, let us assume at any moment VO output is equal to plus V supply, positive. Okay. So, this is positive and this is okay, this is at 0 volt. So, this is input, call it V I, and this you can call V P. Now, output is positive. Say if input is 0, okay, if say input is equal to 0 volt, then this is 0, this is positive. What will be V P? It is some sort of average of these two voltages V I and V O. You know, this is nothing but, okay, let me also write the value of V P here. I write V P is equal to V I R 2 V I R 2 plus V O R 1 plus V O R 1 whole divided by R 1 plus R 2, a weighted average of V I and V O. This is V P. Now, if input is 0 volt, then V P will be positive. This is positive. So, you are assuming this is positive, V supply. So, this is positive, this is 0. So, this will be positive, of course. Okay. So, this implies V P greater than 0, positive, and if this is greater than 0, the static characteristic of op amp says this is greater than V n. So, output will be positive, output will remain positive, output will remain at positive value. Now, say I make input greater than 0. So, this is positive, V P will of course be positive, and therefore, output will remain positive. Now, say I make input less than 0, then what will happen? If it is slightly negative, but this is sufficiently positive. Okay. So, here you can see this is slightly negative, this is sufficiently positive. So, their combination can be still positive. So, this can still be positive. So, output will remain positive. So, that means slight negative input will not change the output. So, I have to make input sufficiently negative enough, so that this point V P goes below V n 0 volt, then only output will change. So, let me ask the same question. The question is, for what input V O will change or will become. So, right now it is positive, will become negative. Let me make some space. Okay. So, this is the question, for what input output will become negative. Answer. What is the answer? I have to make it sufficiently negative, so that V P is slightly lower than 0 volt, and then the output will change. Okay. So, what is the boundary condition? The boundary condition is that the value of V P should be so that, value of V I should be so that V P is equal to 0 volt. That is the boundary condition. Okay. So, the boundary condition is the condition when V P will be equal to 0, exactly equal to 0. Okay. We actually need V P to be slightly less than 0. Okay. You can write it slightly less than 0. So, this implies, let me write the value of V P from this. So, V I R 2 plus V O R 1 divided by R 1 plus R 2. This should be slightly less than 0, which will imply, now this you can forget the denominator. So, this will imply V I R 2 less than V O R 1. Vi R2 less than minus Vo R1. Okay. So, from this I can write Vi is less than Vo R1 by R2 minus. This is the boundary condition. So, if you make V, and what is the value of Vo at this moment? V supply. Okay. So, I can write this as V supply. So, this is the boundary condition. If you make Vi lower than this, then output will go from positive to negative. Okay. Similarly, now once this is already negative, okay, then what will happen? Okay, now let us see. So, now this is, now output is already negative. Now, Vo is already negative. Okay. So, this is minus V supply. Now, I will ask again the same question. For what input output will become positive? Will become positive. So, that is the question. Okay. So, for what input output will become positive? So, it will become positive when this Vp goes above 0 volt, this is 0 volt. So, Vp has to go above 0 volt. So, that means, so the answer Vp has to be greater than 0 volt. Now, what is Vp? Vp is nothing but Vo. So, we have it here. Okay. So, let us put that value Vo R1 plus Vi R2 divided by R1 plus R2, this has to be greater than 0. So, which means this has to be greater than 0. Okay. And at this moment Vo is equal to minus V supply. So, from this I can write V minus V supply R1 by, this is greater than 0, this is the condition. Okay. So, this is the boundary condition, okay. And since Vo is equal to minus V supply, so from this I can write that Vi has to be greater than, I bring this on that side, so it becomes plus V supply R1 and divided by R2. So, this is the condition. Okay. So, let me write the rule for this circuit, this second circuit, circuit 2. Okay. The rule for circuit 2 output will become positive when input goes above this V supply R1, goes above V supply R1 by R1 plus R2. Similarly, output will become negative when input goes, let us see, it is written here, minus V supply R1 by R2, below Okay. So, that means this I can call the upper trigger point, this I will call the lower trigger point. Okay. So, once again, if I give this input, the question is how will the output look like? Okay. So, for this circuit, you see output will become positive when input goes above the upper trigger point. Okay. So, this is the upper trigger point, which is same as V supply R1 by R1 plus R2. Okay. Somewhere here I will have V supply, somewhere down there I will have the value minus V supply, and this lower trigger point is equal to minus V supply R1 by R1 plus R2. Okay. Now, if the input goes above this, output will become positive. So, here it will become positive. I do not know what it was before this, but here it will become positive. And it will remain positive until and unless input goes below this value, which is here. So, here it will go negative like this, and here it will become positive again like this. Okay. So, you observe output increases when input increases. Okay. You see here input is increasing, output is also increasing. Similarly, here you see input decreasing, output decreasing. So, there is a correlation between the input and output, unlike the previous circuit where the thing was reverse. So, here output also decreases when input decreases. Okay. So, we call this circuit, it is a non-inverting type Schmitt trigger. So, circuit 2 is a non-inverting Schmitt trigger, CHMITT trigger, because input and output changes together, one increases, so the other also increases. Okay. But the previous one, as I said before, that was a inverting Schmitt trigger. Okay. So, let me conclude this video, this class, by saying that so what have we done in this class? We have drawn initially two amplifier circuits, non-inverting and inverting. Then we have swapped the plus minus inputs here as well as here as well as, and we said that this acts as a Schmitt trigger where the output can be only positive or negative, positive V supply or negative V supply. And we have asked a question that for what value of input the output will change from positive to negative or negative to positive, here as well as here. So, for what input output will become positive to negative and negative to positive. To find that, you simply have to consider the rule of the op amp, which says output becomes positive if V p is higher than V n. So, find out the value of input which will make V p higher than 0 volt or lower than 0 volt. Similarly, here you know in this circuit V p is at this voltage which depends on V supply. So, find out the value of input which will make the input lower than V p or higher than V p, so that the output becomes positive or negative. Okay. So, this is what we have seen, and these transition values of input we have called their upper trigger point or lower trigger point. Okay. Yes, and last thing, as you know that the hysteresis band, okay, hysteresis band is what? Is the gap, as we have defined before, between these two values, upper trigger point minus lower trigger point. So, therefore, for this circuit, this will become 2 V supply R 1 by R 1 plus R 2. Similarly, you can find the hysteresis band for the other circuit. And one important point, last thing, in this circuit, which was originally a non-inverting amplifier, we have modified it. This becomes a inverting type Schmitt trigger, which means output decreases if input increases. On the other hand, in this circuit, which was originally an inverting amplifier, when we change the plus minus sign, this behaves like a non-inverting Schmitt trigger, which means output also increases if input increases. Thank you.